Now, in the previous session, I was towards the end in such a rush to finish because my Chinese wife had just arrived and she was waiting patiently in the front door. So, in my rush, I left out a paragraph that was on the board, so I'll mention that now. Now, it involves the eta, a label on your transition. And the eta is characteristic of non-deterministic finite automata, NFAs. Okay, so now it's a bit tricky. It's a little bit more complicated than in the case of DFAs, deterministic finite automata. And I will, let's see, next session we will see the actual use of this eta in a concrete case, so you'll get a hang of how it's done. But I can give you an idea of how it works. So say you've got, say you have you have transitions like this between states. But let's say one of the symbols, well, let's say one of the labels on a transition is eta. I mean, there may be others, but let's say there's an eta here. When you see that, and it's in the context of NFAs, right, non-deterministic finite automata. So when you see this, what you do is the following: you split. So you magically create another copy of your whole machine, your whole automaton, right? And you put there are two copies. Okay, so well, you make a copy of the one you had. So you have two copies, and in the first copy you put the current state at J, and without waiting for reading the next symbol, very important, note what I've just said. Okay, without waiting for the reading of the next symbol, you create. You make a copy, so you have a second version of the second machine, and you put its current state at K. Okay, all at the same time. So, so you were at some state here, whatever it was, right? And you transition to J, and then you have a look. In a sense, you're looking ahead at the next transitions, in a sense. And if you see an eta like this, then you split your machine. Meaning you make a copy of it, and you put the current state of one of those two machines, one of them in state J, and the other one, the other copy, you put its current state in state K. Okay, hope that's clear. You may wonder why on earth you do that. Well, its justification will come later as you see how useful this device, this trick is. Okay. Now, if there's more than one transition coming out here, also with an eta on it, well, you just do the same thing. So you would make a second copy and put its state as current state as L. Okay, so as you come from this state here, whatever it is, to here, and you see these two etas, then instead of having like one machine, that bang, suddenly you've got three in three different states. Okay, one of them will be in state J, another one will be in state K, and a third one will be in state L. Right? That's how this eta trick works. Okay? And you'll have an extra copy of the machine for each branch, or for each transition that has an eta label. Okay. All right. Now. I was mentioning a little bit in the previous session that you can look on non-determinism, or rather non-deterministic computation, as a kind of parallel processing. You have various branches just working away independently of each other. And for example, the eta, that creates copies of the machine. If you have more than one for a given current state, if you have more than one symbol for if you have more than one copy with the same symbol as an exit arrow, then also you copy. You make a copy of the machine, and one machine will branch one way, and another copy of the machine will branch the other way. So there's like two circumstances where you're making these copies of the machines. One is what I've just said, when you have more than one exit arrow that has the same symbol on it, some symbol from your alphabet. That's one way. And the other way is with this eta trick, right? So you're in some state here, you transition to this state, so that will become your next state. But there's also these two etas, let's say. So you'll make two more, you'll make a copy due to this transition, and make another copy due to this transition. So you'll have two more machines, two more DFAs, sorry, NFAs, okay? And you'll put the current state in your first copy as K, and the current state of your second copy, so your third machine, as state L, right? So, due to these two ways that you're making copies, you get branches, and once the branch is established, they just proceed on independently of each other. So, if you start at the top here, say at the root node, that's the starting state, and let's say time is going down vertically. And so every time you branch, you get a splitting, a forking, if you like. A fork like the old forks centuries ago. I think they had just two prongs. So you'd put your fork into your meat instead of picking up with your fingers. You'd fork it like that. So to fork means like to split, go two ways. But since then, modern forks tend to have four prongs. Okay, so. You can look on computation. Now there's two broad categories, right? Deterministic computation. So your next state is determined. It's fixed. There's no choice. There's no branching. You for a given current state and a given input symbol that you're reading, then in deterministic computing, with certainty, you know the next state. Okay? So if you look on sort of like the history of transitions of states, like if you start here and time going down this way, then in deterministic computation you just go from one state to the next, right? Until you get to your final state, and then depending on whether the final state is in your set of accept states or not, the DFA, because this would be a deterministic machine, it either accepts or rejects. Okay, so the history of state change, if you like, is just like a line, like a rope. There's no branching. Right? You can't have any branches because then it would not be deterministic. Deterministic means there's only one choice for the next state. Right? Whereas non-deterministic computation, you can get branchings, right? And each time you get a branching or a forking or whatever, you get a copy made of your machine, and then and you'll put the current state of that the copy in a certain state, and then off it goes. In a sense, starting with that state that you put into it. Yeah. So like if you again with time going this way, and you start at your start state, you start in a given state as you. I mean that and that are the same in the sense you start in just one state for both deterministic and non-deterministic. But then as time goes on, going this way, as you're transitioning from one state to the next, you may get branching. So the history of the whole thing, the whole computation, this looks more like a tree, right, in a technical sense. So okay, so look on non-deterministic computation as a kind of tree-like structure as parallel computation, as various branches. They just proceed on independently of the others. Okay, and you remember the last comments I was making. previous session, that when you've read your last symbol in the string, the input string, if just one of these branches in your NFA, non-deterministic finite automaton, so long as one of them, at least, of those branches terminates, if its final state belongs to one of the accept states, then just one of them, or more, but at least one. If one of those branches terminates in an accept state, then the whole machine, the whole thing, is said to accept that state. Right? That's the power of an NFA. And latest session or two, I'll start listing some of the advantages of, in fact, superiorities of NFAs compared to DFAs. Obviously, there's been some point to doing this. Like we got stuck before. Remember, we're trying to prove that the class or the set of, what was the technical term? Regular languages is closed under the operation of concatenation. And we started the proof and then we got stuck. Well, we're going to use non-deterministic computation. We will use an NFA to solve that problem. It's a few boards away, but we're going through this rather long diversion, in a sense, from that proof, with the NFAs, non-deterministic finite automata. Okay, so NFAs tend to have a tree-like history, and DFAs tend to have a linear string, like a linear history, sort of like a rope. Right? Okay.